about equilibrium, what does it mean to you? Tell me, Hala. When we say equilibrium, what does that mean to you?
Uh, a balance
Yeah,
of
that's
some
good.
sort, yeah.
Good. All right, here we go.
Hello, everyone, and welcome to Unit 1, Lesson 2. This lesson is on dynamic equilibrium in chemical systems. So let's get started. Hello, everyone, and welcome to Unit 1, a CH4U intro lesson. This lesson is on careers in chemistry. Hello, everyone, and welcome to Unit 1, Lesson 2. This lesson is on dynamic equilibrium in chemical systems. So let's get started. Further, here are the rest of Hello, everyone, and welcome to Unit 1, a CH4U intro lesson. This lesson is on careers in chemistry.
Okay, so for this curriculum, the expectations are, so we are basically relating science to technology, society, and environment. We are going to be analyzing the optical conditions for a specific chemical process to happen, and related to the principle of equilibrium.
Of our curriculum expectations, which you can read over on your own. Further, here are the rest of our curriculum expectations, which you can read over on your own.
So we're going to do some developing skills of investigations and communication. We're going to use appropriate terminology related to chemical systems and equilibrium. We're going to also be demonstrating an understanding of the concept of dynamic equilibrium and the variables that causes shifts in the equilibrium of chemical systems.
More specifically and more importantly are our learning goals and success criteria, so students will be able to explain the concept of dynamic equilibrium and describe the Chatelier's principle. And success criteria, by the end of this lesson, you should be able to use examples of chemical and physical equilibrium systems and show how it applies to changes to a chemical reaction at equilibrium. Equilibrium, by definition, is a state in which there are no observable changes as time goes by. So chemical equilibrium specifically is achieved when the rates of the forward and reverse chemical reactions are equal and the concentrations of the reactants and products are remain constant. They don't change.
Okay, so at equilibrium, closed systems, no matter like energy, pressure changes, and no macroscopic changes, reactants and products both present and usually in different amounts. Reactants equal constant, product equal constant. Uh, they can be approached from both sides. Rate of forward reactions equals rate of reverse reactions. Reversible reactions. So sometimes products of a reaction react with each other to reform the reactants and the reverse reaction. A reversible reaction is one that proceeds in both forward and reverse directions. Dynamic equilibrium, a balance between forward and reverse processes occurring at the same rate, and this is denoted by a double arrow. As you can see here, this double arrow. Oh, why isn't this playing? That's so weird. Okay, I don't know why this is not working. It's not saying anything. So weird. I'm gonna refresh this page and see what happens.
Yeah, it just sometimes doesn't work. I mean, the past 2 days it used to give me a blank screen, so at least it shows something.
Mhm.
It used to tell me cannot load the domain.
Mhm.
Yeah, in general, just did not work. Gave me a gray screen, and was like, but didn't get much done this week.
Hello, everyone, and welcome to Unit 1, Lesson 2. This lesson is on dynamic equilibrium in chemical systems. So let's get started. Hello, everyone, and welcome to our Unit 1 SCH4U intro lesson. This lesson is on careers in chemistry. Further, here are the rest of our curriculum expectations, which you can read over on your own. More specifically and more importantly are our learning goals and success criteria. So students will be able to explain the concept of dynamic equilibrium and describe Le Chatelier's principle and success criteria. By the end of this lesson, you should be able to use examples of chemical and physical equilibrium systems and show how it applies to changes to a chemical reaction at equilibrium. Equilibrium, by definition, is a state in which there are no observable changes as time goes by. So chemical equilibrium specifically is achieved when the rates of the forward and reverse chemical reactions are equal and the concentrations of the reactants and products are remain constant. They don't change. We can be talking about physical or chemical equilibrium. Physical equilibrium is in a closed system. You are switching, back and forth between just the physical state of matter. So on your reaction side, you have H2O in the liquid form, and then your product side, you have H2O in the gaseous form, in the gas form. Whereas chemical equilibrium, an actual chemical reaction has occurred, right? So there's forward and reverse reactions of a chemical reaction. It's not just a change of state. So for example, we have nitrous oxide, N2O4, being converted into NO2. So there are a couple of requirements in order for a chemical reaction to be in equilibrium. First, it has to be a closed system, meaning there's no matter, no energy, or no changes in pressure throughout the reaction. There's also no macroscopic changes, microscopic changes. And then the reactants and products are both have to be present, usually in different amounts, but that's fine. And then the concentration of the reactant is constant, and the concentration of the product also remains constant. So again, it's a closed system. You're not adding in any matter, any energy, or any changes in pressure. And the rate at equilibrium or dynamic equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. So you can, to help picture dynamic equilibrium, right? Think of this. Imagine 18,000 people attending a sporting event. Most of them are in their seats for most of the time, but there's always about 400 people at the concession stand buying snacks, let's say. This means that on average, about 17,600 people, right, minus 18,000 minus 400, are in their seats. Right, so throughout the event, people continuously move back and forth from their seats to the concessions, but the total number in each area still remains constant, right? It's a closed system in dynamic equilibrium. And by definition, a reversible reaction is a chemical reaction that proceeds in both the forward and reverse directions, setting up an equilibrium in a closed system. Right, so the reaction rates in the forward and reverse directions are equal, and so a constant concentration of reactants and products will always be present. Right, and those reversible reactions are identified by that double arrow symbol in your chemical formula or your chemical reaction formula. So again, to reiterate, dynamic equilibrium is when you have that balance between the forward and reverse processes occurring at the same time, and that's that double arrow that you see here. So for example, H2O in the liquid state can yield H2O in the gaseous state, or it can go vice versa from a gas to a liquid. So an example of dynamic equilibrium, another example similar to that stadium arena example, is a closed bottle of pop. Right, so you have carbon dioxide gas in a closed bottle of pop, leaving the dissolved state, entering a gas state. But at the same time, you have the CO2 gas leaving the gas state and entering a liquid state. You have no visible changes in the pop. It's not a chemical reaction. It is just a physical reaction or physical equilibrium. So that forward reaction in an equilibrium equation is left to right, or we always read just like you would read anything from left to right. And the reverse reaction then is right to left. And then chemical reaction equilibrium is that dynamic equilibrium between the reactants and products of a chemical reaction in a closed system. So not just like a physical reaction, a chemical reaction. And there's three different types of equilibrium that we're going to talk about. First is solubility equilibrium. That's like the dissolving process. You have phase equilibrium, which is the change of state. And then you have chemical reaction equilibrium, which is an actual chemical reaction that goes both ways, right? Reactants to products and then products to reactants. So talking about solubility equilibrium, recall that solubility is the quantity of a solute that dissolves in a solvent under specific conditions. For example, the amount of sugar that can dissolve in water at 100 degrees. Right, so solubility equilibrium is a dynamic equilibrium between a solute and a solvent in a saturated solution in a closed system. And then phase equilibrium is a dynamic equilibrium between different physical states of a pure substance in a closed system. So looking at this figure here, and the first picture, so when you add a solute into a solvent, right, many more of the, let's say you have crystal ions dissociate from the crystal, then will crystallize into it, right? Because they want to mix with the solute that you first added. So for example, when a solid ionic compound such as silver iodide dissolves in water, those ions are going to be removed from the crystal as they become surrounded by the water molecules. And the reverse reaction also takes place, eventually reaching equilibrium, right? So figure B, as more ions come into solutions, more ions crystallize. And then at solubility equilibrium, right, we've reached our max solubility, the solute ions dissolve and are dissolving and crystallizing at the same rate. And we can refer to a solution as a saturated solution when it contains the maximum quantity of a solute, right? So beyond that solubility limit, any added solute will remain solid and not dissolved because we're at our max solubility limit. So the maximum amount of solute that can dissolve has dissolved. And recall the kinetic molecular theory that you learned about last year, which states that particles are always moving and colliding even if no changes are observed. So dissolution is also another word we use for the process of dissolving. So when we've reached that solubility limit, we can call that a saturated solution. Moving on to, again, phase equilibrium, right? A dynamic equilibrium between changes in physical states or different physical states of a pure substance in a closed system. And a closed system, right? A system, it may exchange energy, but not matter with its surroundings, right? So for example, a closed bottle of pop, it's a closed system. It can exchange heat, right? If you take it from the fridge and put it on the counter, it will cool off or it will lose heat, but it's still a closed system, right? You didn't take off the lid, no gases are escaping or coming in. And an example of phase equilibrium we've already talked about is H2O from the liquid state to the gaseous state, or the solid state to the liquid state and vice versa. And recall that chemical equilibrium is reached when that rate of the forward reaction equals the rate of the reverse reaction. So if we have hydrogen gas, that's iodine gas, yielding to HI, hydrogen iodide, at the same rate that we have hydrogen iodide dissociating or decomposing into the separate hydrogen gas and iodine gas. And the delta H value is the amount of energy required, and it's always referring to the forward reaction. So 13 kilojoules of energy is said to be liberated for every mole of hydrogen iodide formed in this reaction. And then for the whole reaction, back and forth, our delta H, the amount of energy required is negative 26 kilojoules. So looking at an example of a chemical reaction equilibrium in a closed system, we have N2O4 gas yielding 2NO2 nitrous oxide, or vice versa, right? The forward or reverse reaction. So in figure A here, we see the N2O4 in equilibrium with the NO2. And in this graph, when N2O4 is introduced into a closed container, right, its concentration will decrease rapidly because the reaction is going from left to right. That's that red line. As the concentration of NO2 increases, that blue line, right? So we're going from reactants to products. At the same time, we're going from products to reactants. However, as soon as the concentrations of both the N2O4 and the NO2 change more slowly, they will change until equilibrium is reached, and that's that dotted vertical line, right? So from this point on, when we're in equilibrium in a closed system, the concentrations will no longer change with time. And again, this is just showing the text for the figures we talked about on the previous slide. One thing to note is that the same dynamic equilibrium composition will be reached regardless of if you start from the forward reaction or the reverse reaction, right? So an equilibrium position can be reached starting from either the forward reaction or from the reverse reaction. So considering the equation we had just looked at between dinitrogen tetraoxide gas, the N2O4, and nitrogen dioxide gas, the NO2, if the reaction will progress to chemical equilibrium, whether you go the forward reaction or the reverse reaction, or a mixture of the two, right? Provided that the environment, system, and total mass remain the same. So we can also calculate percent reaction at chemical equilibrium. And we can describe the state of equilibrium in two ways. So percent reaction or using the equilibrium constant. And percent reaction is the yield of product measured at equilibrium compared with the maximum possible yield of product. So like theoretical versus actual yield, or the equilibrium constant. So we'll talk about each of those. So chemists have studied the reaction of hydrogen gas and iodine gas extensively. Because these molecules are relatively simple and the reaction takes place entirely in the gas phase. When the hydrogen and iodine are mixed, the reaction proceeds really rapidly at first, so that initial dark purple color of the iodine vapor fades and then becomes constant. And the color of iodine vapor is the really only easily observable property here. So that reaction is H2 plus I2 yields 2HI. And we are going to take a look at this reaction further to calculate our percent reaction. So using this reaction, and this table contains evidence from 3 different experiments involving hydrogen iodine system, one in which hydrogen and iodine are mixed, one in which hydrogen iodine and hydrogen iodide are mixed, and one in which only hydrogen iodide is present initially. And this is at a temperature of 448 degrees Celsius. The system quickly reaches an observable equilibrium each time. And chemists will use these measurements, such as the ones in the table here, to describe the state of equilibrium in 2 ways, right? Percent reaction or in terms of the equilibrium constant. So let's move on using these values. So doing an analysis of the concentration values from system 1, so that first row in that table, shows us that at 448 degrees Celsius, it reaches an equilibrium, approximately 78% of the maximum possible yield. And that's this reaction or this calculation we're going to go through, right? We can calculate the theoretical yield here stoichiometrically as if the reaction were quantitative and moving in the forward direction. Right, so in this example, we would expect 2.00 millimoles per liter of your HI based on the mole ratios of the chemical reaction and that concentration that we started with. So the actual yield was 1.56 millimoles per liter, as you see in your table. And we do a percent reaction, which equals actual product yield over the theoretical product yield times 100. So we have 1.56 from our equilibrium system concentration of HI over 2.00. If you would expect to have, that's your expected, your theoretical yield. And you get 78%. Right? So 78% is your percent reaction of your hydrogen iodide system at 448 degrees Celsius. Just a reminder that that theoretical product yield of hydrogen iodide, that 2.00, that value was obtained from your mole ratios and your stoichiometric calculations. So going back to that chemical reaction, right, the balanced chemical reaction of hydrogen plus iodine gas yielding hydrogen iodide, right, it's a 2-to-1 ratio of HI to H2. So you can calculate your amount of HI following those mole ratios from your chemical reaction, giving you 2.00 millimoles per liter of hydrogen iodide. Another thing to talk about is classes of chemical reactions. Well, first of all, all chemical reactions are considered to be reversible. The question is not whether reactions go in both directions, but to what extent they go one way or the other. So reactions can fall loosely into three categories. Reactions that favor the reactants very strongly, that favor the products very strongly, or reactions that achieve noticeable equilibrium conditions. All right, so looking at this table, reactions that, or you can just have no reaction, right? No reaction. Reactions that favor the reactants very strongly, the percent reaction, that value that you calculated, is much less than 1%. So in these reactions, mixing the reactants has no observable result. In contrast, reactions that favor the products very strongly, where the percent reaction is more than 99%, and these reactions are observed to completion. And these reactions are generally written with a single arrow to indicate that the effect of the reverse reaction is pretty much non-noticeable. And then you have reactions that achieve noticeable equilibrium conditions. So the percent reaction lies somewhere between 1 and 99%. And in these cases, significant amounts of both reactants and products are always present in the mixture in a closed system. Right? If it's slightly less than 50%, the reactants are favored. If it's greater than 50%, the products are favored. So this table shows us how percent reaction is used to classify equilibrium systems, and how this classification is communicated when you're looking at reaction equations. And typically that percent reaction value, so that 78% we just calculated in the previous example, is usually written above the equilibrium arrow in a chemical reaction. So as you learned and talked about in previous chemistry courses, right, doing stoichiometric calculations are pretty easy and straightforward when the reactions proceed all the way to completion, right? All of the reactants become all of the products. However, when reversible reactions achieve equilibrium before all of the reactants become products, the stoichiometry requires a little bit more thought. So we use something called an ICE table, an ICE table, or initial change equilibrium concentrations chart or table, which is a convenient way to organize information needed to solve a stoichiometric problem involving equilibrium systems. Right, so ICE, initial change equilibrium, refers to those values that are included in the table. And for systems composed of aqueous solutions or gases, I means initial concentration of the reactants and products, C stands for the change in concentration of the reactants and products, like between the start of the reaction and the point at which the equilibrium is achieved, which is considered, I guess, the end of the reaction. And then E stands for the concentration of the reactants and products at equilibrium. So here's an example of an ICE table for the reaction we've been talking about, hydrogen gas plus iodine gas yielding hydrogen iodide. So we have our ICE initial concentration, the change, and your equilibrium concentration as we go through the reaction for each of those values, for each of our products and our reactants. Let's look at an example of calculating our concentrations at equilibrium. Consider the following equation. H2 plus F2 yields 2HF. If the reaction begins with 1 mole per liter concentration of hydrogen gas and fluorine gas, and no concentration of hydrogen fluorine or products, calculate the concentrations of hydrogen gas and hydrogen fluoride gas at equilibrium. If the equilibrium concentrations of fluorine gas is measured to be 0.24 mole per liter. And so we can first list the information given in the question. We write out our ICE table. We know the initial concentration of hydrogen gas and fluorine gas to be 1 mole per liter, so we can put that in our first row. And we know of our initial concentration of hydrogen fluorine gas to be 0, right? We're not starting with any, our reactants only, so that's 0 moles per liter. And then we know we were given our concentration of fluorine gas at equilibrium to be 0.24 moles per liter. So we set up our ICE table to organize that first row of information, and that's 0.24 for fluorine in the equilibrium, that last row. So we can then use some variables and use our stoichiometric relationships between each of the products and reactants to figure out our answer here. And so by the time equilibrium is reached, a certain amount of hydrogen gas and fluorine gas will have changed into hydrogen fluoride. And our balanced equation is in a 1:1:2 ratio, right? Indicates that this change occurs in a 1:1:2 molar ratio. So for every mole of hydrogen gas and fluorine gas that react, 2 moles of hydrogen fluoride are formed. We don't know the exact amounts, right? But we can choose the variable X to represent changes in the concentration of these reactants and products. With the coefficients of X corresponding to the coefficients in the balanced equation, right? Since hydrogen gas and fluorine gas are consumed in a 1:1 molar ratio, the change in concentration is represented by minus X for each hydrogen gas and fluorine gas. Moving on, then, the balanced equation indicates that 2 moles of hydrogen fluoride are produced for every mole of hydrogen gas and fluorine gas that react. Therefore, we represent that change in concentration of hydrogen fluoride to be plus 2X. So in the final concentrations of hydrogen gas and fluorine gas is going to be their initial concentrations, which was 1, minus X. So almost think of each column as a math problem, right? 1.00 minus X is equal to your equilibrium concentration of 0.24. And then for that last, for our HF, it's 0 plus 2X is equal to, that would be what your answer is. So we can calculate that, but we need to know the value of X. Right? Knowing that our equilibrium concentration of fluorine gas is 0.24 moles per liter, right? That was given. We can determine the value of X. We can use that second column of fluorine gas and say 1 mole per liter minus X equals 0.24 moles per liter. Rearrange that for X and we'll get 0.76 moles per liter. We can then use that and multiply it by 2 for our final concentration or equilibrium concentration of hydrogen fluorine gas, right? Because that's 2X, so 2 times 0.76 moles per liter, we get 1.52 moles per liter. So again, we're just using a variable and using our coefficients in our stoichiometric equation. Our final example. When ammonia is heated, it decomposes into nitrogen gas and hydrogen gas according to this equation. When 4 moles of ammonia is introduced into 2-liter rigid container and heated to a particular temperature, the amount of ammonia changes to 2 moles or to 2 moles. Determine the equilibrium concentration of the other two entities. So we can first get, so our initial amount of NH3 is 4 moles, and it gets converted into 2, right? So our initial is and our final equilibrium amount of ammonia is 2, and our initial is 4. So we can set up our ICE table. Notice then that which is shown here, that the multiples of x correspond to the coefficients in the balanced equation. 2NH3 yields N2 plus 3H2. So a coefficient of our reactants is going to be minus 2x and our products plus x and plus 3x. So it's a 2 to 1 to 3 ratio. Our initial concentration of ammonia is 2 moles, and our equilibrium concentration is 1 mole. And we get that using our concentration of our initial, which was 4/2, giving us 2 moles per liter, which then at equilibrium, right, 2 moles over 2 liters of that rigid container, that's 1 mole per liter. That's our equilibrium concentration. We can then determine the value of x, right, using the initial, change, and equilibrium values in our ICE table of NH3, of our reactant. And when we do that, we get x to be 0.5 moles per liter. And we can use that value of x, multiply it by the coefficients to get our final equilibrium concentrations, which we get 0.5, and then 3 times 0.5 is 1.5. So the concentration of N2 is 0.5 moles, and the concentration of H2 is 1.5 moles. And that's all for this lesson. Have a great day.
Okay. Hella, are you there? Hella? I can't hear you. Hella?
Yes.
Are you there?
Yes.
Okay, perfect. Sorry, I couldn't hear you earlier.
That's
Okay,
fine.
so at the end of this lesson, you have an activity, and go ahead, work on that on your own. Activity lesson. And it's a downloadable worksheet. And go ahead and answer all these questions. You can refer back to the lesson that we covered. Okay? And then you can go ahead and turn that into me, and then there's also going to be a multiple choice quiz that you're going to be doing. Sounds good?
Yes.
Okay, awesome. So we're going to work on that. You have spring break next week. If you want to take the time to do it then that'll be great. And also, were you able to work on the lab safety and career exploration and presentations from last time?
I did the quiz.
Okay. Okay, let's see.
I got like an 80 on that one. 8 out of 10.
All right.
The worksheet, there was I've also finished the WMS
You
and
have,
safety worksheet
okay.
for,
So will you be able to scan that and email it to me?
yeah,
Okay, and then there was a multiple choice
the
quiz there too.
that quiz is done. I've also finished that one. It's an 80, I think.
Oh, perfect. All right, good job.
The presentation, I'm working on it
All right.
for chemistry jobs.
Okay,
I'll be
wonderful.
finished by tomorrow, hopefully.
Okay, wonderful.
I've also started the the significant figure quiz. I should be submitting that also like by the end of today.
Excellent.
Since, yeah, it's a tab opened. I have too many tabs.
All right.
And yeah, I think that's all you asked for last time.
Yes, yes. Good
Yeah.
job. So yeah, good job keeping up with your homework and the quizzes. Same with that equilibrium system. And now we're gonna go on to Lachar Taylor's principle.
Okay.
Okay, here we go.
Hello, everyone. Welcome to Unit 1, Lesson 3. We are talking about Le Chatelier's principle today. So let's get started. So our curriculum expectations are posted here to analyze the optimal conditions for a specific chemical process related to the principles of equilibrium, use appropriate terminology related to chemical systems and equilibrium, and show your understanding of dynamic equilibrium and the variables that cause shifts in equilibrium of chemical systems. And most importantly, our learning goals and success criteria. Students will solve problems pertaining to equilibrium systems, apply Le Chatelier's principle in a simulated activity, identify common equilibrium constants, and by the end of this lesson, you should be able to analyze various factors affecting chemical systems at equilibrium, use the equilibrium constant formula, and use your ICE tables again. So Le Chatelier's principle states when a chemical system at equilibrium is disturbed by stress or change, the system adjusts or shifts to oppose the change. Right? So the system adjusts in a way that opposes a change, and this principle was developed in 1884 by a brilliant French chemist, Henry Louis Le Chatelier, who made many observations of chemical systems at equilibrium. Developing this generalization, which has become one of the most powerful laws in science. And the application of this principle involves an initial equilibrium state, a shifting non-equilibrium state, and then a new equilibrium state, right? Because you have a change, you have an a reaction at equilibrium, you apply some sort of change, so you have a shifting non-equilibrium state, and then you have a new equilibrium state. Stresses or these changes can be concentration, change in pressure or volume, and change in temperature. So we'll talk about each of those. So the first one is Le Chatelier's principle with concentration changes. So the principle predicts that if more of a reactant is added to a system at equilibrium, then that system will undergo an equilibrium shift or a movement of the system at equilibrium, resulting in a change in the concentration of reactants and products. So the effect of adding more of a reactant, for example, is that we first observe the reactant concentration decreasing as some of the added reactant gets converted to product. And this period of change ends with the establishment of a new equilibrium state, which the concentrations are usually different from their original value. So the system changes in a way that opposes the change. So increasing the concentration of the reactants or decreasing the concentration of the products will favor the forward reactions, causing the equilibrium to shift to the right of this hypothetical equation here outlined in red. In contrast, decreasing the concentration of the reactants or increasing the concentration of the products will favor the reverse reaction, causing the equilibrium to shift to the left. And recall that the additional removal of solid or liquids does not change the concentration and does not cause a shift. So this only applies to gases and aqueous solutions. Here's a graph showing that shift in equilibrium to a new equilibrium. So you have a hypothetical reaction A plus B yields C plus D. And so the reaction has an initial equilibrium, which is then disturbed at a specific time indicated by the vertical dotted line by the addition of some more reactant. In this case, more of B is added, that green line. Right, some of this B reacts with A, so increasing its concentration of our products. So the concentration of both products increases until a new equilibrium is established. Right, so the concentrations eventually become constant again at a new level. So looking at another example using nitrogen gas plus hydrogen gas yielding ammonia, NH3, you can see in our concentration versus time graph, we have our initial equilibrium values in the white column of hydrogen gas, ammonia, and nitrogen gas. And then we have the unequilibrium phase, and that's that first dotted line where we add some hydrogen gas. So hydrogen gas is added, and then that yellow area, that yellow shaded area is showing that middle unequilibrium state of change. And then slowly as that extra hydrogen gas gets converted into ammonia, we reach a new equilibrium, which is at a different level. The final concentrations of each of those reactants and products is different, but we've reached a new equilibrium, and that's that blue, purpley shaded section of the graph. The second change we can have is a change in pressure. So according to Boyle's law, if you remember from last year, right, the concentration of a gas in a container is directly related to the pressure of the gas. That was from grade 11. So decreasing the volume of something to half its original value will double the concentration or the pressure of gas in the container. Right, so changing the volume of any equilibrium system involving gases may cause a shift in the equilibrium. So if you increase the volume, you're going to be decreasing the pressure because there's more space for the gas molecules to spread apart. But if we decrease the volume, you're then increasing the pressure. Now to reiterate our changes with pressure, increasing the volume of the container, or in other words, decreasing the pressure, will cause a shift to the side of the equation with more gas molecules. So in our example, it will shift to the left, right, because you have 4 moles of reactants versus 2 moles of our products. In contrast, decreasing the volume of the container, or in other words, increasing that pressure, will cause a shift to the side with less gas molecules. So in our example, it will shift right, because you have 4 on the left and 2 on the right. 2 moles of each. Looking at this example, we have 2 SO2 plus O2 gas, oxygen gas, yields 2 SO3 plus energy. So if we look on the left side of our reaction, we have 2 moles of SO2 and 1 mole of O2. So there's 3 moles on that side, and there's just 2 moles on our product side. Right, so the equilibrium is disturbed by a decrease in the volume of the container, right, at that time indicated by that vertical dotted line in the graph. So therefore the equilibrium shifts forward, right, towards the products. The concentration of SO3, your product, increases, while the concentration of the reactants decreases until that new equilibrium state is established. And then we have changes in temperature. So the energy and chemical equilibrium equation can be treated as though it were a reactant or a product. So recall endothermic and exothermic reactions. An exothermic reaction is where the energy is released, and an endothermic reaction requires the input of energy. And so energy can be added or removed from a system by just heating or cooling the container. In either situation, the equilibrium will shift to minimize that change in temperature. If the system is cooled, it will try to warm itself, and the equilibrium shifts in the direction that produces heat. Okay, so that would be the exothermic. If heat is added, the equilibrium shifts in the direction that absorbs heat. Okay, so the opposite. So increasing the temperature will cause a shift to the left, and decreasing the temperature will cause a shift to the right. So the reaction establishes an equilibrium that is disturbed by a decrease in temperature. The equilibrium shifts forward, increasing the concentration of SO3, while decreasing the concentration of both reactants until that new equilibrium is established. And in contrast, in an endothermic reaction, increasing the temperature would cause a shift to the right, and decreasing the temperature will cause a shift to the left. Right? Remember, if the system is cooled, the system tries to warm itself, so it's going to shift in the direction that produces heat. If heat is added, the equilibrium will shift to the direction that absorbs heat. So when the system at equilibrium is heated, the reaction shifts to the right, increasing the concentration. And that new equilibrium gets established. And recall that K is our equilibrium constant. This is the value obtained from the mathematical combination of equilibrium concentrations. And our equilibrium constant is temperature dependent. Therefore, changes in temperature are going to affect what the equilibrium constant is. If we shift to the right, we increase the amount of products and we're increasing our equilibrium constant. Whereas if we shift to the left, the rule is that you're increasing your reactant, so you're decreasing your equilibrium constant. So we've looked at 3 changes that have an effect on the equilibrium of the chemical system, right? Concentration, energy changes, pressure and temperature. So concentration, right, pressure, volume, and temperature. But there are other changes that can happen that have no effect whatsoever on the equilibrium position of a chemical system. And here there's 2 that we're going to talk about. One is adding catalysts. Catalysts are used in most industrial chemical reactions and in biological systems as well. A catalyst decreases the time required to reach the equilibrium position, but it does not affect the final position of equilibrium. It increases the reaction rate by lowering the activation energy of the system, so both forward and reverse directions equally. So it decreases the time required to reach equilibrium, but again, like I said, does not affect the final position of equilibrium. forward and reverse rates are increased equally with the catalyst. And then we also have adding inert gases. So the pressure of the gas system at equilibrium can be changed by adding a gas while keeping the volume constant. But if the gas is inert in the system, for example, if it is a noble gas, like an unreactive gas, or if it cannot react with the entities in the system, the equilibrium position of the system will not change. So increase the pressure will increase the reaction rate, increase the probability of successful collisions for both the products and the reactants equally. And so the presence of an inert gas changes that probability of successful collisions between the reactants and products equally. So it doesn't shift the equilibrium system at all. Here's a figure showing the difference between a catalyzed and an uncatalyzed reaction. So in this graph here, the catalyzed reaction is the green line and the uncatalyzed reaction is the red line. So you can see a catalyst reduces the activation energy by the same amount, whether the reaction proceeds from the right or from the left. But that final equilibrium, that thick black line, is still the same in both cases, right? It does not affect the relative concentration of the entities. Here's a nice figure, a summary figure of the variables affecting chemical equilibria. And so concentration, temperature, and volume that we looked at, and then the two variables that do not affect equilibrium, the addition of catalysts or if we have inert gases present. And it tells you which type of change, if you increase or decrease concentration, temperature, or volume, and then what the response is to that system. So a nice summary table for you. So now that we're familiar with these changes in equilibrium systems a little bit more, we can quantify them and we can predict how much of the reactants will be consumed, how much of the products will be formed in any chemical system that reaches equilibrium. And we can use stoichiometric techniques to do these calculations. And these are some general steps for calculating equilibrium concentrations from your equilibrium constant and the initial concentration. So if you're given those, you can calculate our equilibrium concentration. First, you're going to want to balance the chemical equation, and we'll go through some examples soon. Next, determine your Q, your quotient, to see which way the reaction will proceed to get to equilibrium. 3, define the changes needed to get to equilibrium. And again, we can use variables. We can use X to represent the change in concentration. Write the expression for equilibrium constant K. Number 5, substitute the expressions defined in step 3 into the equilibrium constant, and then solve for X and then plug your value back into the table made in step 3. So here's some general steps for you, and we'll go through some examples. Looking at an example, at 1,280 degrees Celsius, the equilibrium constant, K, for the reaction is 1.1 times 10 to the negative 3. And the reaction is Br2 yields to Br. If the initial concentrations are as follows, the initial concentration of your reactant is 0.063, and your initial concentration of your product, Br, is 0.012, calculate the concentrations of each of these at equilibrium. So again, let X be the change in concentration of Br2 here. We're going to draw out our ICE table, initial change in equilibrium. So we know our initial. We are given our initial concentration, 0.063 and then 0.012. For Br2, our change is going to be minus X. And then our equilibrium is just going to, we're going to create an expression for that like we did in the last lesson. So 0.063 minus X. For Br, we know we have a 2 coefficient there, so our change is going to be plus 2X. So our expression for the equilibrium row will be 0.012 plus 2X. And we haven't talked about our equilibrium constant expression yet. We will after this example, but you have your K subscript C, and that is going to be your BR2 over your BR, your product, sorry, so your reactant over your product. You're going to sub in your expression for each of those, and you solve for X, and we'll continue, we know it's equal to 1.1 times 10 to the negative 3. So we're going to rearrange that expression to solve for X, and we'll continue on the next slide, and then we'll talk more about how we got that formula. When we have our expression here, in this case, we need to employ the use of the quadratic formula, ax squared plus bx plus c equals 0. And we're going to use our quadratic formula here, x equals negative b plus or minus b squared times the square root of negative 4ac all over 2a, if you remember from lovely math class. When you plug in those values, you get two values here, those circled in red, negative 0.0105. or x equals negative 0.00178. So when you plug each of those values into our expressions, the answer we're going to take is the one that's positive, right? The one that is the 0.0648, if you remember how to use your quadratic. Formula. We're going to reject the negative one because we can't have a negative concentration, right? So therefore, x is going to equal 0.00844. So here's that slide I was referring to for how you know what your equilibrium constant formula, so your K formula, is going to be when you have a chemical reaction. And so no matter the starting composition of reactants and products, the same ratio of concentrations is achieved at equilibrium. So for a general reaction, the equilibrium constant expression you have is A, so or little a, some coefficient of A, your first reactant, plus B is some coefficient by your second reactant B, yields P plus Q, and then the coefficient little p and little q, whatever the coefficient or the ratios are of those. So then your Kc, or your equilibrium constant, is going to equal P times Q over A times B, with the coefficients from your chemical reaction becoming the superscripts in your equilibrium constant. So if there's 2 in front of A, it becomes A squared in your equilibrium constant expression. Looking at an example here, N2O4 yields 2NO2. So our K expression is going to be NO2 squared over N2O, concentration of N2O4. Let's say that's equal to 4.63 times 10 to the negative 3. And another example, if we have a chemical reaction, A plus B yields C plus D, and we have the lowercase letters are our subscripts, our coefficients. Those become the superscripts in our law of mass equation here, our equilibrium constant equation. So C, superscript little c, times the concentration of D, superscript little d, over the same with our reactants. If a very large K value means that the reaction is favoring the products, and a very small K value means the reaction is favoring the reactants. So again, to reiterate this magnitude of K, when your equilibrium constant is very large, the equilibrium lies very much to the right, so the products are favored. And when your equilibrium constant is very small, the equilibrium lies very much to the left and the reactants are favored. However, when it's neither very large nor very small, so it's approximately equal to 1, neither the reactants nor the products are favored at equilibrium. Right, so very small, your reaction proceeds hardly at all. it's sort of in the middle. You have appreciable concentrations of both reactants and products. But if it's very large, your reaction will proceed nearly to completion, right? It lies very much to favoring the products. So here's looking at an example of calculating the value of the equilibrium constant for the decomposition of ammonia. And in this case, even though our question doesn't give us those three concentration values, because that part's not pasted in the slide here, but those values are given to you. So you're given the concentration of N2, of H2, and of NH3. So you would just simply write out your equilibrium concentration or equilibrium equation, right, with the product on the top, reactants on the bottom, and those values are given to you, the 1.5 times 10 to the negative 5 times 3.45 times 10 to the negative 1 cubed, and then all divided by 2.00 times 10 to the negative 4 squared, right? So even though those values, where I'm getting those values is they were from the previous question, which wasn't included in the slide. And then we solve for K, which is 15.4. And again, this slide is a nice way of reviewing the magnitude of your equilibrium constant and what that means. Right, so if K is much greater than 1, the reaction proceeds towards completion. The concentration of products are much greater than the concentration of the reactants when we're at equilibrium. If K is approximately equal to 1, then the concentrations are approximately equal as well. But if K is less than 1, so we have a very small amount of products formed, the concentration of the reactants are much greater than the concentration of the products at our equilibrium. And just two different types of equilibrium or special terms of equilibrium to review. There's homogeneous equilibrium or heterogeneous equilibrium. So a homogeneous equilibrium applies to reactions in which all of the reacting species are in the same phase, right? So they're all gases in this case. And then a heterogeneous equilibrium applies to reactions in which all reactant species are in different phases. It's not all the same phase. So, for example, calcium carbonate is a solid, but then carbon dioxide is a gas. All right, and that's it for this lesson. I'll see you next time.
Okay, Hella, are you there?
Yes.
Okay, perfect. So that was the end of video lesson. Go ahead. This was Le Chatelier's principle. There's an activity that's associated with it. And if you can go ahead and basically do that multiple choice quiz after that. Okay. So the two lessons that we did today, and we're going to focus on, I mean, there's just a lot of calculations and everything associated with it. So I want you to give all your focus on these two. So the chemical equilibrium systems and Le Chatelier's principle. So yeah, study them more on your own, and also make sure that you do those activities at the end of each of these two lessons. Let's see, lesson 4. Since we do have a little bit of time, I was going to ask you, do you have any questions?
Not at all. I've actually also started going through the textbook.
Okay.
Since, I learned better from the textbook. So
Okay.
I've already kind of know the chemical equilibrium, the dynamic equilibrium, the equilibrium position, and the reversible So basically 7.1, a chapter.
Mm-hmm.
One question is, when might the test be? And when might midterms be?
So I will let you know. I'll make a note of that and I will let you know about that.
Yeah, chemistry is one of my top 6, so I need them to actually be out with the school midterms.
Mm-hmm.
Yeah, so that university can see them.
Gotcha.
Yeah, another thing is that if my mark ever goes down below the 95 point, please do warn me.
Okay.
Yeah, because I need that higher than 95.
Gotcha.
Kind of unrealistic, but it's a necessary goal.
Yeah. Okay, sounds good. I will let you know and just yeah, keep up with all your like all of your assignments, the activities, and you said that you made 80s on your quizzes, so that's good.
Yeah, I got 2 mistakes on the first quiz.
All right. Let's see. So you want to know when the midterms are? We'll let you know, like we'll announce it. So,
Okay.
yeah. So those are quite heavy lessons. I want you to kind of focus on them. Lesson 2 and lesson 3. And then we have the next lesson we have is solubility equilibrium and acid and base equilibria. We're going to do, right now, I think we should just stick to 2 lessons at a time. And then we'll go from there. Does that sound good? Do you want me to review anything?
Not at all.
Okay. All right. Let's see here. Well, since let's see, we do have 1 more hour, almost an hour, 45 minutes to go. Do you want to go ahead and start on lesson 4?
Yeah, sure.
Let's do it. Okay, there we go.
Hello, everyone, and welcome to Unit 1, Lesson 4. We'll be talking about solubility equilibrium today, so let's get started. So first, a review of our curriculum expectations. To conduct an inquiry to determine the value of an equilibrium constant, solve problems related to equilibrium using calculations, identify common equilibrium constants, and write the expressions for each. More importantly, our learning goals and success criteria. Students will be able to explain equilibrium concepts relating to solubility, solve problems pertaining to molar solubility and KSP, and explain the common ion effect or success criteria. You can do this, you'll achieve these learning goals by using your ICE tables and analysis of precipitation, formation, and solubility equilibrium systems, and by writing the expressions for KEQ, KSP, and KW. So a special case of equilibrium involves any situation where excess solute is in equilibrium with its aqueous solution, right? So previously we talked about solubility. And you can establish such an equilibrium between solute and the solution either by starting with excess salt and dissolving it until the solution is saturated, or by mixing solutions of 2 salts together that results in a product precipitating out of a solution or forming a solid. And once precipitation ends, the remaining solution is said to be saturated, right? And the dissolved ions will form a dynamic equilibrium with the precipitated crystals. So not all ionic compounds are equally soluble. The dissociation of ionic compounds is reversible. So for example, we can have calcium chloride as a reactant yielding or dissociating into its separate ion state, calcium 2+ and chlorine, or vice versa, right? You could have your calcium ion and your chlorine ion coming together to form calcium chloride, which is a solid or precipitate. So like I said, equilibrium can be reached between the solid substance and its dissolved ions up to the saturation point. And the solution is saturated. For solubility equilibrium, the solution is saturated when it's at equilibrium. So no more ions can dissociate. So for any solute that forms ions in solution, the solubility equilibrium constant is the product of the concentrations of the ions in the solution raised to the power equal to the coefficients of each in that balanced equation, right? Just like what we did in the last lesson. So we often call that the solubility product constant, just like our equilibrium constant in the last lesson. This is symbolized as KSP, K lowercase or K subscript SP. So the solubility product constant is an equilibrium constant applied to the solubility of electrolytes. It's equal to, like I said, the product of the concentrations of the ions raised to the power of whatever the coefficients are in the balanced chemical equation. And by definition, when we refer to a common ion, we're referring to an ion that is common to both salts in a solution. So for in a solution of silver nitrate with silver chloride, for example, Ag+, silver or silver ion would be a common ion. And the common ion effect is a decrease in the solubility of an ionic compound caused by the addition of a common ion. So we'll talk more about the solubility product constant as we get going. Looking at an example, we have silver chloride, which is a solid, yielding its dissociated ions, silver plus and chlorine minus, Cl minus. So our solubility product constant, or our regular equilibrium constant, if you follow the same rules from our last lesson, is the concentration of Ag+ times the concentration of Cl minus all over the concentration of your silver chloride. But recall, since silver chloride is a solid, the concentration is not changing. Remember, this only applies for aqueous or gases. So it's built into the K value. So we can take that part out. It's already included in our KSP value. So the new constant is the solubility product constant, or KSP. So without the concentration of our solid, it's just the concentration of your silver ion times the concentration of your chloride ion. So for example, lead 2 chloride has a molar solubility of 1.62 times 10 to the negative 2 moles per liter. What is the KSP, or the solubility constant, of this salt? So we read out our chemical reaction, right? Lead chloride yields our ions. We dissociate our ions. So Pb2 plus 2 Cl minus, we balance it. So it's a 1:1 to 2 molar ratio. And then we write out our KSP. Our KSP expression. We know lead chloride is a solid, so our equation is just going to be Pb2, the concentration of Pb2 plus times the concentration of Cl minus to the power of 2, because the coefficient in the chemical equation is 2. And since we have a 1:1 ratio between the concentration of our reactant and our lead ion, we know that those are both going to be equal to 1.62 times 10 to the negative 2 moles per liter. However, our concentration of our chlorine ion is going to be 2 times that amount, right? Because there's a coefficient of 2. So 2 times 1.62 times 10 to the negative 2 moles per liter, and you will get 3.24 times 10 to the negative 2 moles per liter. When we plug in both of those values into our solubility equation, so we plug in the concentration of Pb2 plus times the concentration of Cl minus to the power of 2, we get our solubility product constant of 1.7 times 10 to the negative 5. For our second example is the KSP of silver chloride is 1.8 times 10 to the negative 10. What is the molar solubility of the silver chloride? So we're sort of like working backwards. Not a lot of knowns here, but we know the KSP, and we know our KSP equation is going to be the concentration of Ag plus times the concentration of Cl minus. So we can just put each of those as X. Those are unknowns. We know the KSP is 1.8 times 10 to the negative 10. X times X is X squared. We can take the square root of that to just get X by itself. And we get 1.34 times 10 to the negative 5. Everything's a 1-to-1 ratio, so that's going to be the solubility of the AgCl. And there's your answer. Another thing I want to mention is the size of the solubility constant depends on the solubility level of that salt. So a large KSP, the concentration of ions at equilibrium is high, so the salt is very soluble. A small KSP, the concentration of ions at equilibrium is low, so the salt has a low solubility. It doesn't want to dissolve in its solution very much. Another thing we can do with our KSP values is predict precipitation. So recall we learned that reaction quotient Q is a value that can be used to calculate whether or not a system is at equilibrium. We can also use the reaction quotient in the context of solubility, so our QSP. And we can use it to predict whether a precipitate will form when we mix solutions of metal cations and non-metal anions together. So we can calculate Q to determine whether, after mixing, the ions are present in too high a concentration, in which case a precipitate will form. So this reaction quotient, we can call our solubility quotient, or we also sometimes call it our trial ion product, right? The reaction quotient applied to the ion concentrations in a salt. So to predict whether a precipitate will form, when solutions containing anions and cations are mixed, we compare the KSP value for the salt of these ions to Q. And as we know, the value of KSP equals the ion product of a saturated solution where the dissolved and undissolved solutes are in equilibrium. So if our QSP is less than our KSP, we'll have a shift right to get to equilibrium. So all the solid is dissolved. There's no precipitate. If our QSP is greater than our KSP, we shift left to equilibrium. A precipitate will form in that case. Or if it's relatively equal, then we're said to be at equilibrium, or it's saturated and there's no precipitate. So the common ion effect. When equilibrium exists in a solution involving ions, or the equilibrium can be shifted by dissolving into the solution anything else that adds more ions, adds a common ion, or any compound that reacts with one of the ions already in the solution. Okay, so adding an ion to a solution that already contains an ion will affect the solubility. And how so? Well, the equilibrium will shift away from the added ion. Remember the opposite effect. Remember Le Chatelier's principle. So this common ion effect is a reduction in the solubility of a salt caused by the presence of another salt having a common ion. So we're lowering the solubility of an ionic compound by adding another common ion. So here's an example of the effect of a common ion on solubility. Here we have our lead chromate, and we have our ions, our lead ion and our chromate ion. So if sodium chromate solution is added to a saturated solution of lead chromate, it provides a common ion, which is that chromate, CrO4 2-, and this causes the equilibrium to shift to the left. Right? So solubility decreases, and then more solid lead chromate precipitates. And here's our KSP, our solubility constant expression, the concentration of lead times the concentration of our chromate ion. So if the concentration of the CrO4 goes up, and the concentration of lead must go down, right? Because it's a constant, it's equilibrium. And here's a really important table, excuse me, that you can refer back to. This is the table of sample solubility product constants, simple KSPs at 25 degrees for a variety of different solutes, right? So you can refer back to this table to get those K values for any of these solutes. Recall again, determining whether you'll get a precipitate or not. You get a precipitate when the concentrations of the ions exceed the solubility of the ionic compound. So if we compare that Q value with the current solution concentration, or to that value of KSP, we can determine if precipitation will occur. If the Q value is equal to our K value, the solution is saturated and there'll be no precipitate. Right? But in contrast, if Q is less than KSP, the solution is unsaturated, no precipitation. But if our Q value is greater than KSP, we'd be above saturation, and that salt that is above saturated will precipitate. However, some solutions in this instance will not precipitate unless they are disturbed, and these are called supersaturated solutions. Right? In a case where our Q is greater than K, but a supersaturated solution is unstable. So the solute concentration exceeds the equilibrium concentration, but it might not necessarily form a precipitate. So overall, precipitation will occur if your Q value is greater than your KSP value. And here's an example of your supersaturated solution. And it will precipitate, in this case, a seed crystal is added to the solution, and then you get the precipitate formed, right? Without that, if it's just sitting still and not being disturbed, it might not form a precipitate. But that is not the most common circumstance. If Q is greater than KSP, you will likely get a precipitate. Let's look at an example of determining whether a precipitate occurs. The concentration of calcium ion in blood plasma is 0.0025 moles. If the concentration of oxalate ion is 1.0 times 10 to the negative 7, do you expect the calcium oxalate ion to precipitate? And our KSP is 2.3 times 10 to the negative 9. So the three steps we're going to follow is first, determine the initial concentration of the ions. Then you need to find your Q value, and you need to compare that with your KSP value. So let's take a look here at solving this problem. Our QSP, it's the same formula that you're going to use for the KSP, but the only difference is that, right, for our reaction quotient for Q, it's similar to K. The difference is that K is calculated using concentrations that are for sure known to be at equilibrium, whereas Q, they may or may not be at equilibrium, but we use the same mathematical equation to calculate it. So in this case, our Q value is the concentration of your ion, Ca2+, times the concentration of C2O4 to minus, and it's a 1-to-1 ratio. When we multiply those values, our concentration of our calcium ion is 0.0025, and the concentration of our calcium oxalate, or sorry, our C2O4, is 1.0 times 10 to the negative 7, our oxalate ion. So we get our Q value of 2.5 times 10 to the negative 10. And we compare that with our KSP, which was 2.3 times 10 to the negative 9. And therefore, since our Q value is less than our KSP value, no precipitate will form. However, when we're applying this criteria for determining if you have a precipitate, the effect of dilution when solutions are mixed must also be considered, right? When you mix two things together, they are diluted in some way. So for example, a 250 milliliter sample is 0.0012 molar of lead nitrate is mixed with 150 milliliters of 0.064 molars of NaI, sodium iodide. Should precipitation of lead iodine occur with the KSP of 7.1 times 10 to the negative 9? So we calculate the new concentrations in total volume, and a total volume of 400 milliliters, which is 0.4 liters. Right, we have 250 milliliters being mixed with 150 milliliters. Concentration of lead, our lead ion, is 0.025 times 0.012, all over our total amount is 0.4 liters, and we get 7.5 times 10 to the negative 4. The same thing for our iodine ion, 0.15 liters times 0.0640 moles, and divided by our total amount of liquid, we have 0.4, and we get 0.024 moles. So our QSP is the concentration of our lead ion times the concentration of our iodine ion, which are those two values we just calculated, multiplied together since the iodine ion is also to the power of 2. We get 4.32 times 10 to the negative 7. Compare that with our KSP. Our Q value is greater than our KSP. So therefore, a precipitate will form. And something else just to touch upon briefly here, we can actually compare solubilities, but which salt will be the most soluble in water? That's the one with the highest molar solubility. And what we've done in this example, and don't worry too much about this, because we've created an expression for KSP for each salt using X. So our KSP of CUS of number 1 will just be X squared, whereas Ag2S, silver sulfide, is going to be 2X because Ag2, and then squared becomes the coefficient, becomes a subscript, times X. Whereas our number 3, our Bi2S3 is going to be 2x squared, 3x cubed. So we get 108x to the power of 5. When we solve for x for the molar solubility of each of those, we get the one with the highest molar solubility being number 3. Looking at an example, calculate the molar solubility of zinc hydroxide at 25 degrees Celsius, where your KSP is 7.7 times 10 to the negative 17. And here's our formula. It's a 1 to 1 to 2 ratio. So our solution is as follows. We want to find the molar solubility of zinc hydroxide. Our KSP equation, right, is going to be those two gases, those two aqueous products, the concentration of our zinc ion and our hydroxide ion. And in this case, we're going to use X again to quantify this a little bit better. We know the concentration of our OH is 2. It's in a ratio, our two products in a ratio of 1 to 2. So our concentration of our hydroxide ion is 2 times the concentration of our zinc ion, right? It's double. So if we can plug that in, we can plug the 2 times the concentration of the zinc ion for our hydroxide concentration. So we get a KSP is equal to the concentration of zinc times 2 times the concentration of zinc again. Right, so we're reducing the number of variables so we can solve for this better. We know our KSP is 7.7 times 10 to the negative 17. When we multiply that together, we get 4 times the concentration of zinc to the power of 3. All right, so then our concentration of zinc is the cubed root of 7.7 times 10 to the negative 17 divided by 4 equal to 2.7 times 10 to the negative 6 moles per liter. And since we're in a 1 to 1 ratio, the concentration of our zinc hydroxide is going to be equal to the concentration of our zinc ion, so it's going to be the same. So the molar solubility of zinc hydroxide will be 2.7 times 10 to the negative 6 moles per liter. Alternatively, we can solve this using an ice table, whatever you prefer. So we'll go through that example on the next slide. So here's our ICE table for calculating our KSP. I always actually prefer to use the ICE table. It makes a little bit more sense for me, but however you would like to do it mathematically, that's fine too. So we have our initial concentration, our change in concentration, and our equilibrium concentration of Averroes zinc hydroxide. Right, those are all unknowns. But our starting of our zinc and our hydroxide ions is 0 and 0, our initial concentration. Our change is going to be based on our mole ratios. In this case, for zinc plus X, for hydroxide plus 2X. Right? So our equilibrium concentration will be 0 plus X, or just X, for zinc. And for hydroxide, it will be 0 plus 2X, or just 2X's again. So our KSP is the concentration of zinc, which we just quantified as X, or equilibrium concentration, and our concentration of OH hydroxide squared is 2X. We have 2X squared, and that's equal to 7.7 times 10 to the negative 17. X times 2X cubed, we get 4X, or times 2X squared, sorry, we get 4X cubed. So we need to solve for X there. So we're going to be square rooting our KSP and dividing by 4 to get X by itself. And again, we get 2.7 times 10 to the negative 6. That's another way to solve for that problem. That way makes a little bit more sense to me, but like I said, you can use the way on the previous slide as well. And that's it for this lesson. I'll see you next time.
Okay, Hella. So we are done with lesson 4 for the solubility equilibrium, and there's an activity associated with it. Okay, and this is your activity. It relates back to the lesson 4 that we just finished. You can refer to your textbook as well. And go ahead and turn that into me, and then also there's a multiple choice quiz at the end of it too. Okay,
Hello, everyone, and welcome to Unit.
sounds good. Hella, are you there?
Yes.
Okay. All right, excellent. So the important thing to take away from this lesson is, you use ICE tables, and you can by analysis of precipitation formation in solubility equilibrium systems, and also to be able to write expression for K equilibrium, KSP, and KW. Okay. So those are your goals for that. Okay. Now we go on to let's go ahead and do lesson 5 as well, since we have some time. Okay, in that way we should be done with equilibrium, the different types of equilibriums. Okay. Hella, are you there?
Yeah.
Okay. So with this lesson, you should be able to explain the Bronsted-Lowry theory of acids and bases, and you should be able to use ion product constant for water. So that's our goal. And here we go.
Hello, everyone, and welcome to 5. Today we're talking about acids.
Go sleep.
Let's get started.
Nighty nighty.
Oh, Hella, you're not mute.
Oh, sorry about that.
It's Okay.
Hello, everyone, and welcome to Unit 1, Lesson 5. Today we're talking about acid-base equilibrium. So let's get started. As always, here's your curriculum expectations. So analyze the optimal conditions for a specific chemical process related to the principles of equilibrium. Use appropriate terminology related to chemical systems and equilibrium, and solve problems related to equilibrium by performing calculations. And then to identify common equilibrium constants and write their expressions.
Okay, so these are your expectations for this topic. So again, lesson 5, acid-base equilibria. Here we go.
More importantly, your learning goals and success criteria. Students will explain the Bronsted-Lowry theory of acids and bases and use the ion product constant of water, or Kw. In your success criteria, you'll do this by finding the conjugated acid-base pair and by calculating pH, pOH, H3O plus, and OH minus, the concentration of those for a chemical reaction. So acids and bases, you should be pretty familiar with what acids and bases are. You started learning about that in grade 10. They are electrolytes that form aqueous solutions, and they have unique properties. Right, acidic solutions, remember, like vinegar, are sour tasting, they conduct electricity, where basic solutions also conduct electricity, but are generally bitter tasting and feel slippery. And we can characterize acids and bases in terms of chemical properties as well. Acids are solutes that produce hydrogen ions, H plus ions. In aqueous solutions, while bases produce hydroxide ions, or OH minus ions, when dissolved in water. So acids have properties, right, due to that H plus ion. They turn litmus paper red if you were doing a pH test, and bases have the properties due to the presence of the OH minus hydroxide ion, and they turn that litmus paper blue if you were doing like a lab an acid and base test.
Okay, Hala, I have a question for you. Hala?
Yeah, for sure.
Okay, so for acids, you know, when we have litmus paper, right? So it's a paper that basically
Yes.
detects whether if it's an acid or a base. If it turns blue, would you think that that's a base or an acid? If it turns blue, would
If
it
it
be?
turns blue, it means basic.
Yep, good job.
It's a
And
base.
then, yep. And then what about if it turns red? Would it be a base or an?
Acid.
Yep. All right, good job. All right, here we go.
So these first classifications of, or characterizations of acids and bases was done by an individual called Arrhenius, which is why we call it the Arrhenius theory of acids and bases. Right, the model adequately explains the properties of most acids and hydroxide bases, but it has some limitations and it fails to properly account for basic properties of compounds that don't have the hydroxide ion. For example, ammonia, NH3. Ammonia is a base, but doesn't have a hydroxide ion. So this Arrhenius theory is not fully comprehensive. Instead, we have a Bronsted-Lowry theory, which we're going to talk about instead. So H plus is a bare proton, does not exist in water. It is attracted to a lone pair of electrons on oxygen in water, forming a hydronium ion, H3O plus. Right, and again, like I said, it fails to explain why ammonia, example, a base that doesn't have that hydroxide ion, is still basic. And as well, some reactions take place without any liquid involved, such as the one right there. So it's not always, we don't characterize acids and bases always as just an aqueous dissolving in water or aqueous solutions. So the Arrhenius theory, again, states that acids generate H+ ions in water and bases generate hydroxide ions in water, but the Bronsted-Lowry theory is just in terms of protons. So for example, when hydrogen chloride reacts with water, a proton is transferred from a hydrogen chloride molecule to a water molecule, forming a hydronium ion, that H3O+, and a chloride ion. Right, so hydrogen chloride acts as a Bronsted-Lowry acid, whereas water, the one accepting the H+, acts as a Bronsted-Lowry base. Right, so according to the Bronsted-Lowry theory, acids are H+ donors and bases are H+ acceptors. So the Bronsted-Lowry theory recognizes an acid-base reaction as a chemical equilibrium. So it has both the forward reaction and a reverse reaction involving the transfer of that proton. Right? An acid is a substance from which a proton can be removed, or a proton donor, and a base is a substance that can accept a proton. Right? And that proton is referring to the nucleus of a hydrogen atom. That H+ we call a proton. So in a proton transfer reaction at equilibrium, and we're looking at the Bronsted-Lowry theory, both forward and reverse reactions involve Bronsted-Lowry acids and bases. So for example, in this hydrochloric acid solution, the forward reaction is a proton transfer from the hydrochloric acid to the water molecules. And the reverse reaction is a proton transfer from the hydronium ion to the Cl-, or sorry, to the H3O+. So this equilibrium is typical of all Bronsted-Lowry acid-base reactions. There's always going to be two acids and two bases in any acid-base equilibrium. We call this a conjugate acid-base pair. And we'll talk a bit more about that. So in our Hello everyone and welcome to Unit 1, Lesson 5. More important to ask. So the Bronsted-Lowry. So in a proton transfer reaction at equilibrium, and we're looking at the Bronsted-Lowry theory, both forward and reverse reactions involve Bronsted-Lowry acids and bases. So for example, in this hydrochloric acid solution, the forward reaction is a proton transfer from the hydrochloric acid to the water molecules. And the reverse reaction is a proton transfer from the hydronium ion to the Cl-, or sorry, to the H3O+. So this equilibrium is typical of all Bronsted-Lowry acid-base reactions. There's always going to be two acids and two bases in any acid-base equilibrium. We call this a conjugate acid-base pair. We'll talk a bit more about that. So in our Bronsted-Lowry definition, here's our reaction. We have HCl plus NH3 yields Cl- and then NH4+. The acids donate protons. So we know the hydrogen from HCl is being donated to the ammonia. The base accepts the proton. So our HCl is the acid and our NH4 or NH3 is the base. And like I said, this is called a conjugate acid-base pair, right? A pair of substances whose molecular formulas differ by a single H+ ion or a proton. It's called a conjugate acid-base pair. So two substances in an aqueous solution whose formulas differ by an H+. The acid is the more positive species having the extra H+, right? Because donate, are the ones that have the extra H+ and donate the H+ to the base. So we have in our reaction here, we have our acid HCl plus our base NH3, and then the conjugate base is our Cl-, right? The one that gave up the H+, and our conjugate acid is the one that then gained the proton. Looking at another example, an acetic acid molecule and an acetate ion are a conjugate acid-base pair. Acetic acid is the conjugate acid of the acetate ion, and the acetate ion is the conjugate base of acetic acid. Right? And then the hydronium ion in water is the second conjugate acid-base pair in this equilibrium. And here's another example looking at ammonia NH3 plus H2O. NH3 is our base, H2O is our acid, and then the conjugate pair, so of ammonia, our NH3 is the base. It is paired with the conjugate acid, which becomes the NH4+, right? It gained a proton but it was a base, so it's the conjugate acid. And then the initial acid, which was the water, which we know is the one that's going to give up that H+, its conjugate pair is a conjugate base, which then becomes OH-. And this theory can help explain examples that the Arrhenius theory, the original theory, cannot. So we use the conjugate acid-base pair, Bronsted-Lowry theory. And here's the table showing conjugate pairs and different or common acid-base reactions. So there's 6 different reactions listed here, and they just help you identify which one is the acid. So the acid is listed first in all of those reactions, followed by the base. And then you have the conjugate base and then the conjugate acid. It's showing you the red is our one conjugate, or red is the acid, blue are the bases. So then one red goes with one blue, right? The acid is conjugate pair with its conjugate base. And then the initial base on our reactant side of the reaction is conjugate pair with the product that ends up as the acid. So another way to look at it is that the conjugate base remains after it's what remains after the H+ is lost. So if our acid is HCl, the conjugate base is Cl-. And then our conjugate acid is what remains after the H+ is gained. So if our base in our reactants is NH3, the conjugate acid of that is NH4+. You also have amphoteric substances, and those are substances that can act as either an acid or a base. So water acts as an acid in the presence of a stronger base, but it can also act as a base if it's in the presence of a stronger acid, right? It can become OH- or it can become H3O+. So it is amphoteric. It can be an acid or a base. The autoionization of water is the dissociation of an acidic or basic compound in aqueous solution, producing ions that interact with water. So the pH of an aqueous solution is determined by the position of equilibrium in reactions between the ions that are present and the water molecules. So water is never just a collection of pure H2O molecules, right? Experiments have revealed that some water molecules react with each other to produce hydronium ions, or H3O+, and hydroxide ions, or OH-, according to this equation here. And because the conductivity is so slight, there must be considerably more water molecules than ions in an equilibrium mixture of this reaction at standard atmospheric temperature and pressure. So in every sample of water, an equilibrium is formed between the hydronium ions, the hydroxide ions, and water molecules, but it greatly favors the water molecules. And of the billions of random collisions occurring amongst water molecules, a few are at the right energy and orientation to cause a reaction. So this results in the transfer of a proton, H+, from one molecule of water to the other, producing a hydronium ion and a hydroxide ion. Right, so these collisions, which form these ions, is very rare in water, but it does happen, and this is called the autoionization of water.
Okay, Hella. So it looks like it is 7 now. So since we are out of time, I want you to go ahead and do the activities for the lessons that we did. So that would be lesson 3. Well, actually 2, lessons 2, 3, and 4. So go ahead and work on these activities, okay?
Yeah,
Now-
sure.
So lessons 2, 3, and 4. Next week, we're not going to be meeting because of the spring break starting on the 10th. And yeah, so